Okay, we're finally ready to tackle texture mapping, which will take us quite a while to look at all the aspects of it. But it's the prime digital technique in computer graphics and has taken over a lot of the functionality that we used to have to do with geometry, but now can do much, much better by using a combination of geometry and digital techniques. So we're going to look at some basic strategies for three variants of texture mapping, and I'll show you examples in a minute. Straightforward texture mapping, which is just sort of painting with a digital image on top of some geometry. Environmental mapping, where or reflection mapping, where we try and make surfaces look shiny by putting an image on them that reflects the environment. And bump mapping, which gives the appearance of a surface being very, very detailed and not smooth, although in fact the underlying surface is smooth, and we do it by changing the rendering process. But the basic strategies involve making some decisions about how we really want to do it. Do we want to go forward through the process? Do we want to go backwards from a pixel to find out what color it's going to be? And these are issues that are going to arise again when we look at some implementation issues. Do you start at the front end and with an object and try and figure out where it goes, or do you start at the back end in the frame buffer and go backwards and try and figure out what objects contribute to that to the color of that pixel? And there are different strategies, and they both all have their good points and their bad points. We also want to look at some issues that will arise that'll get us into a discussion of aliasing, where because whenever we go to a sample digital environment, we're going to risk having some aliasing or jaggedness problems because we're no longer working in continuous world, and we have to see how we can do as well as we can without having a tremendous time penalty. So let's start at the beginning and say, well, why don't we just do things the way we have been doing them by just having lots of polygons? And the answer is that even though graphics cards keep getting better and better, and you can easily buy a graphics card where I think now the 10 million polygons per second is probably low for what even a $100 or less graphics card can do. No matter how many polygons we could render per second, there's going to be a lot of phenomena that we just can't model very well with geometry without having almost an infinite number of polygons. And generally they fall under realistic modeling of real phenomena that doesn't really work well with geometry. So if you think of things like trying to model clouds, clouds are pretty complicated. They're these fuzzy shapes. We see dark areas and light areas and clouds behind other clouds, and to try and model that with geometry can be done, but it's really tough. You take another thing and look at grass. All of these thousands or millions of blades of grass in a little area, and you say, well, gee, I want to have a little rectangular area covered with grass. Am I going to model each leaf as some sort of polygonal model and then have millions of them floating around? In general, terrain, when you're talking about mapping applications, you look at Google Maps or something like that, where you put layers on those maps. That's not geometry. You're putting some kind of digital picture on top, because putting that kind of detailed geometry would just be too much of a burden for really any graphics card. And then you can talk about things like skin. How do you model the skin on an animated character to look real? We're getting better at that one. I mean, a lot of that can be done reasonably, but I think probably still more often people will use texture mapping on a very simple model of say an arm or a whole figure, and then do some texture mapping to get the detail of the skin. Well, here's an example, and I'm going to come back to this example a couple of times. And suppose you have an orange. I mean, we all know what an orange is, and what it looks like. And suppose what I'm trying to do is model it. So I can say, okay, first level of modeling is I'm going to make an orange out of a sphere, and we've talked about how to model the sphere recursively or by longitude and latitude. And we make it have the color of the orange, which I could go and measure some way. But you know, that's much too simple. You look at that and you say, no, that's just an orange colored sphere. It's not, doesn't look anything like the fruit. So what if we make the shape a little more complicated? So we make it sort of an oblate spheroid like the Earth, and maybe it curves in at the top where the stem would be. And we could do that with the geometry, but if we get down to really looking at the surface in detail, what characterizes the surface of an orange are these little dimples in the surface, and a lot of them. And how do you model those dimples? Well, if I try and do it with geometry, that's going to say I'm going to model each of these dimples locally by a whole bunch of little polygons in order to make it look realistic and still be smooth and still have all of those dimples in it. That's an awful lot of polygons, and it's just not realistic to think that we can do that. So let's take another view and start from scratch and say, okay, let's take a picture of an orange. And so if we have a photograph of the orange or a scanned orange, then I have a picture of all of that little surface detail, and I could then take that digital image and then try and paste it onto a simple geometric model. Maybe not as simple as a sphere, but perhaps a sphere that's been somehow stretched or scaled a little bit to look more like the shape of an orange. And that act of pasting that picture on is really the essence of basic texture mapping, that we get that detail without having to increase what we say is the geometric complexity of the surface. And that will work, but it won't be quite what we want. And in particular, if I look at one still picture, it might look okay. But as soon as I move that orange, or I move the viewer, or I change the light source, you'll be able to tell that that surface is not really dimpled. It's really a photo which is flat. And you won't see the change in subtle changes in shading that are due to the light or the viewer or the orange being moved. So that later we'll introduce a technique called bump mapping, which is very, very nice for doing this, and in fact is something that we can do in a GPU in real time without much of a performance penalty, and we could not do before we had programmable shaders. So that gets us into the three kinds of texture mapping that we're going to be doing. The basic texture mapping of just using an image to color the polygons that we're going to use in our geometric model, or somehow combine them with other effects such as normal lighting plus have an image mapped on. Environmental mapping is very similar in the way it's carried out, but you're using a picture of the environment around the object. So then we have to say, well, how do I get those pictures? And that'll get us into something we call multi-rendering, where you can use the graphics system to build up these pictures of the environment, then use the pictures to then do a straightforward texture map onto the object. And that'll allow us to do something that we can't do generally without having something like a ray tracer. If we want a highly specular surface that looks like a mirror, what does that mirror do? It reflects the environment. But generally people do that by having some sort of a ray tracing renderer, and this allows us to do it with a pipeline renderer in real time. And finally, bump mapping, as we just said, emulates the lighting at each point by playing around with the normal vectors as you render. So the normal describes what the surface looks like locally. If you modify that normal locally as you're doing rendering, it's equivalent to changing the surface, even though you really haven't changed the surface. You've only changed your normal, and we'll see how that can be done very, very efficiently. So here's a few pictures of what we're talking about. So here's a simple geometric model, and before we, up until now, let's say, this is about the best we could do. We could model it with a bunch of polygons, and we could shade it color, not color. We get you see a specular highlight here. There's some diffuse shading also going on there, but that's about the best we could do. Look at the difference here where we're texture mapping. This is giving it a sort of a rock or granite-like surface, which is something if I tried to model with geometry, this would be pretty complicated. We might have generated this using some sort of a fractal model, but the idea was to make it look like this object was made out of stone, and we did that by using an image that had this pattern in it and then pasting that image on with a basic texture map. So that was done independently. You independently get the picture of the surface, and then independently they'll develop the geometry and then map the image onto the geometry. Now here's an environmental map which is showing the same object reflecting what some environment, where this environment in this case was done by computing it with a separate rendering, but it could have been from a picture, or we'll be talking about this in another lecture or two. And notice how this looks highly reflective, even though it's not been ray traced. Now notice here and in the previous one, these surfaces still look very smooth. And if I do something like move the light or rotate this ball, it'll really emphasize the fact that these are very smooth surfaces. And that may be what I wanted. But suppose I want this surface to have a more complex appearance where it's not smooth but kind of rough. Look at this image. This is a result of a bump map on that same object. Now you look at this and you could swear, hey, this isn't a smooth surface. Look, it's got shadows in here and it looks like it's been kind of etched out a bit. And in fact, if I rotate this object, the light will be reflected in a way or scattered in a way that it really does look like it's a modeled surface. But I guarantee you that this has been done by a variant of texture mapping, and the underlying model is exactly the same model as in the previous slides with a fairly low polygon count. Okay, now, so those are the three strategies we're going to take. And then we'll have a lot of applications of texture mapping. Next question is sort of, where does this take place? This will get us ready for actually looking at how we carry it out in the next lecture. And here the idea is that we do texture mapping, the actual mapping to the surface. We don't do that until we get to the fragment shader. So you can look at the processes. Here's the process we've been talking about till now. We specify vertices and other attributes, and they go through some geometry processing. They go through rasterization, and eventually they come out as fragments to the fragment shader. Now, pixels, or in this case we're going to call them texels, which are really texture elements, which are effectively picture elements, but since we use them for texture mapping, we call them texels. The texels go through really a separate pipeline, which we can think of as just being a very simple pipeline that just brings that rectangular image into the fragment processor, so it's accessible to each instantiation of the fragment shader. Now, also notice that what the implication here, that all of the complexity, because you may be dealing with 1,000 by 1,000 texture map, you don't really use it anywhere in this geometry processing because you don't need the texture values until you're really ready to put a color in the frame buffer. So you only use them in the final stage, and so all of this action is happening in the fragment processor, and that's crucial. It's a crucial reason why programmable shaders are so important, because by bringing this information here and being able to pretty much do anything we want by writing a fragment processor, we can get all of those options and many others without having any kind of fixed function pipeline involved. And this is what we'll be studying in the next few lectures.